So we say that, primitive nth root of unity if the nth power of this guy is 1 and no lesser power, no integer between, strictly between 0 and n is 1. So for example, so if we have a field Q, then e to the 2 pi I over n is a primitive n root of 1, right? And the primitive can be important sometimes. So for example, to kind of push this example, the envelope a little further, if you have e 2 pi I over 6, well, this is a primitive 6th root unity. So this is primitive 6th root unity, but if you lose the powers of it, so these primitive 6 roots, so of course these other 3 are also 6 roots of unity, but they're not primitive, right? So this is actually primitive 3rd. And this is so this one, of course, is -1. Okay. Notice that any field with characteristic not equal to 2 contains the primitive square root, right? Okay. So let me give you the following proposition. Let's suppose that n is a positive integer. And let's say k a primitive nth root of unity. If d divides n, so if d divides n, then n over d is an integer. And if you take your primitive nth root of unity to this power, this is a primitive d root of unity. Number 2, if d divides n, and q is the root of x to the d minus a, some element of X. So this is a particular kind of, root. So notice, essentially, if I take K and I stick on a root of that polynomial, I'm basically joining a radical element, right? An nth root. Then this thing right here, then x to the d minus a has roots in ku. And let me add more of the statement here. And in fact, ku is a splitting field. And xd minus a splits in ku. And if xd minus a is irreducible in kx, then ku is y over k with cyclic y. Uh, any order to be. So let me sketch through some of this proof of one. So notice that eta to the d is this tornado guy to the n of the d to the d power. So in particular, eta to the d is a d through unity. The only question really is why is it primitive? If eta to the e is 1, then certainly this is the case. That has then and this contradicts this tornado guy being a primitive entity. Okay. What about this other business? Let's suppose K contains So my assumption is K contains this primitive nth-root unity. So K contains a d-root unity. Now, of course, if this is a perfect D power, then it's kind of silly. So let's go ahead and assume that this is an irreducible polynomial. What are the distinct roots? Well, if u to the d equals a, right? So that is d is the, or I'm sorry, u is the d root of a, and then u a to u squared u and a to d minus 1 u. Right. All are roots of right, because if you take the d power of all those things, then you get well, you get a u to the d, which is what you need, and you get this eta to a d power times an integer, which is 1. Right? So these are all roots. I think you can agree with that, and are all distinct. Right? Because if eta to the m u equals eta to the k u with m then what happens is u equals eta to k minus mu. And so here we have 1 is equal to this, where k minus m is between 0 and d with the combination. Because primitive eta there. And so these are all distinct roots, right? And so what's my, so I have what, d of them, and they're all distinct, so I've accounted for everybody, right? So that's good to know. This splits in KU. Well, of course it does, because in the splitting field, these have to be the constants that are used in the linear factor. It's x minus u, x minus this, x minus that, and so forth. But these are all in the field, because the field contains a primitive nth-root unity, so it contains a primitive d-root. So good. So what do we got here? Well, now we've got the KU, the splitting field. K, it's the splitting field if it's irreducible. If it's not irreducible, then it already splits down to well, it divides up into smaller polynomials, so you might have smaller intermediate fields. But look, under the assumption that x to the d minus a is irreducible, this is the splitting field of K. Okay, splitting field of x to the d minus a over K. and this is separate. So it's a splitting field, a separable polynomial sub KU. Del Y. Okay. Right. Let's say that the Galois group is cyclic order D, again under the irreducible assumption. So and so why is that?
Just looking at data, so different powers of data.
But I mean, we can actually sort of write down what the automorphism is that sort of runs the show here. Notice that the order Galois group of KU over K is equal to degree KU over K, which is D. So we immediately get that the Galois group has to have order D. And let's look at let's say phi, and notice we'll say phi of u equals, well, where does phi of u have to go? Well, it has to go to another root of this polynomial. So wherever I send it, I'm gonna have to send it one of these things. Well, let me just do the simplest thing. There must be some automorphism, right? Because these are two roots of the polynomial. There must be some automorphism since u to a to u. And I want to investigate this, right? So, excuse me. What happens when I do this again? Pull eta out. Eta is in the base field K. And in general, so in general, we have P M U is so in particular, as defined here, the automorphisms because they all take u to a different primitive root times this, and we've already shown that these are all distinct. So there's d of these. So this is in fact equal to the Galois group of KU over K. So now that I have listed all these automorphisms and there's d of them, it's evident it's cyclic, right? Because it's generated by this. I've run out of real estate. These are all distinct, and it's got to be it because the order of the Galois group is distinct. Okay. Any questions on that? All right. Here is, and I'm gonna do an example here. I'm not gonna prove. I encourage you to kind of try to prove this one. It hinges on this primitive root of unity thing we've done here, and I'm gonna kind of show you an example. I think that sort of illustrates the way that you would prove it and kind of be done with it. Theorem. A 0.7.10. Let F be an extension field of K, where K contains a primitive infinite unity. So, E a primitive root of 1, and I really, it's probably a little sloppy. I mean, I should have built the field before I built the infinite 1, but give me a little slack here. So, we've got some field that contains a primitive nth root of unity. Right. Let F be an extension field. Following conditions are equivalent. Number 1, F is cyclic over K of order where he finds it. So F is a cyclic extension, cyclic Gauss logarithm K of some order D, where D divides the primitive, the order of the primitive root. F is a splitting field. Of a polynomial of the form x to the d minus a in kx. And 3, F is a splitting field polynomial of form x to the n minus b in kx. So we've essentially shown kind of that this implies this. And this is easily recoverable from that too. This is the bigger power. It can be longer. The important thing is the D divides in. In the other direction, see if you can figure that out. Definition. X11. And I don't like this terminology here, but I've got to go with it. Let K be a field. We define a cyclotomic extension of order n. Order n. To be a splitting field of polynomials. Splitting field. Notice this polynomial is just like these ones over here, except we're specializing to a situation where b is equal to 1, right? So in other words, what are the roots? What do the roots look like of this thing? Well, they're the primitive nth roots of 1. Not primitive. They are the nth roots of 1. Some of them should be primitive. By the way, which ones? A little bit more. There you go. Yeah,
It looks like a cyclic group.
a root. Let me see, premise root. Nth root of one, then the R where is that clear to you all? Okay, so I don't prove that. Okay, so, right, so for, these things give you, the list of primitive roots, so. Primitive root one. Then the inference one are given by one these are all the inference of one. How many of them are primitive?
Just spoiling. Yeah.
So there's exactly that many that are primitive. And that is actually important in kind of following up here. Yeah, and this is why I don't really like order in. I guess they've got I wish they'd use a different word for it. But so, for example, if you have a cyclotomic extension of order, or if you have a cyclotomic extension of order 6, right, by this definition here, it's a splitting, let's say over Q. Then it's the splitting field x to the 6 minus 1. But this is not an extension of degree 6, right? And the Galois group is actually smaller, right? So the order doesn't coincide with actually what the degree of the extension of the order of the Galois group is. So that's unfortunate terminology, I'm afraid. Here. Let n be a positive integer and f cyclotomic, K or n. Say cyclotomic is what let's say it is. Where, F is a billion of dimension D. Doesn't have to be a cyclic extension actually, but it's a billion of dimension D. So. Uh. If n is prime, then f is cyclic. Turns out that if n is prime, then in fact this is cyclic, but if it's not, it doesn't have to be. And two is isomorphic to a subgroup of so in any case, the Galois group of ethyl K is isomorphic to a subgroup of the roots of unity of Zn. This kind of ties this thing up about it being prime here, because if n is prime, then the units of this is a cyclic group of order p minus one, right? Right, and if it's isomorphic to a subgroup of this, then it has to be cyclic, right? Because subgroups, cyclic groups, cyclic. Let me kind of give you an example. I'm going to do kind of another long-winded example too. And this is kind of, I think this kind of illustrates what's going on here, but I encourage you to try to work through this yourself. Let K rational numbers need a 12 root of so let F now this is far less than a degree of 12 extension. In fact, we were going to see four. Now, if you believe in this theorem, you can see this because the group of units of Z12, they're just all the cosets that are relatively prime of 12 between 0 and 11, right? So that's what 1, 5, 7, and 11. There's 4 of them. And what's the structure of that? Well, it's group of 4. So if you look at the units of Z-mon 12, just under multiplication, you get 1, 5, because it's 1, 5, 7, and 11. That's a group with 4 elements in it. What's its structure? What's that? Yeah, it is. It's a client core group. Because notice if you square any of those, you get 1. Right? 25 is 1, mod 12, 49 is 1, and so forth. So it's a client core group. So what you're really doing is you're taking the splitting field of, right? I mean, that's what you're doing. We're going to find this kind of explicitly. And this kind of, I think this kind of illustrates what's going on, because on the unit circle, one way to think of this is right. So you can think of this as kind of like 30-degree angle You have to go all the way around, so you get those points on the unit circle in the complex plane. And so there's a lot of sort of redundancy here. And you can see that when you factor the polynomial, this piece is x cubed minus one, x cubed plus one. Going. I have factored this down into irreducible polynomials. Irreducible polynomials over the rationals. And I'll show you where everything shows up. Now, the splitting field has to contain all these. Ooh, look at that. There's one. Look at that, there's negative one. Right there. Look at this one. I negative I. So this comes from this. What about this? This one is minus one. So these are actually the two primitive cube roots of unity. So this one here, and this one here. This comes from x squared plus one. And this comes from x squared plus 1. What about the other quadratic? Well, we've got one of them given us I. This one gives us me the primitive sixth roots of unity. And see what a cheat this is, because if you take a primitive sixth root of unity, right, and you change its sign, you get a primitive cube root of unity, right? So you sort of get that one automatically. And what about this one? Well, that one's the big bad boy. This one gives the interesting ones, right? This one actually gives this one, and this one. And the chordic is the one that's driving the train, because it gives you tornado to 5, tornado to 7, and tornado to the 11. And there's your primitive, there's your primitive roots, right? Notice that the primitive roots give you kind of the other ones, and some of them fall out in a trivial way, some of them fall out with more interesting polynomials, right? But really, so it's actually the splitting field. If you wanted to be more economical about it. That's really what it is. In fact, F is Q. Anybody identify it? Here's kind of another way to look at it. So notice that this field contains this because it contains all the roots, right? Because if you've got radical 3 and I, then you have this for sure. So now you've got everything. And why is the other containment good? Well, because this is an extension of degree 2 over Q when you join a radical 3. And then, of course, this is still real. So when you join I, you get another extension of degree 2. So this is degree 4. Right? And so the Galois group okay. Any questions on that? You feel like that kind of illustrates it a little bit? Yes.
Oh, and these are the cyclotomic polynomials, right?
Yeah, that's right. Okay. Other questions? Okay, so I did promise, and I'm gonna say something about radical extensions here. Let me make a couple of notes in closing before we move on to greener pastures. There is a famous theorem of Crocker and Weber. States that if you have a finite abelian extension of Q, so what do I mean by that? Well, just recall that I mean that F is a finite extension, so it's algebraic. It's also Galois, and it's got an abelian Galois group. Is contained suitable root. Uh, this is kind of a cool theorem because it says that, okay, if you have any abelian extension that you want, if it's got an abelian Galois group, you can find a big enough root of unity to where you can realize that as a subfield of that, which is kind of cool. A word of caution, this theorem does not hold for proper extensions of Q in general. It's true for Q, but not proper extensions of it, which I find kind of interesting. Point 2. An extension f of k if and you're going to see from the definition that all these U's actually have to be algebraic. right? We say F is a radical extension, so implicitly this is a finite extension. You can obtain F from K by joining, elements, and U1, the M1 is in K. And all, K greater than or equal to, some power, well, let's say U to the, J, the NJ is an element of KU1 to UJ minus 1. So it's kind of this recursive thing, right? So there's a power of U1 that's in K. There's a power of U2 that's in KU1. There's a power of U3 that's in KU1, U2, and so forth and so on. We call this a radical extension. There's a radical extension. Okay. Then any element of that sums products quotients of n through. Of elements of well, let me just say in roots. And I'm going to explain this by working through an example. So for example, I might have, and I want to continue this with a good example next time, but if you have an element, so if you have the cube root of square root of 7 equals radical 2 plus fourth root of so I don't mean nth roots as the elements of K, but notice that, so for example, you can get radical 2 in a radical extension, just radical 2. Now, if you have radical 2 in your extension, and then you have 7 plus radical 2. And now you can take that extension here, and it's sort of the same treatment. So you can write elements as nth roots of elements from the previous step. These are called radical extensions. They're the ones that give formulas for roots of polynomials. And we'll talk a little bit about that. Okay, any questions? Let me remind you that Evan Paul has given a talk today on, it sounds like it's going to be really good. It's on quantum computing. I encourage y'all to be there. Other than that, y'all have a good weekend, and we will see you on Monday.